Now the problem says that the heater is here. Let me draw the heater using a purple color. Now, where is the heater? The heater is here, correct? The heater is here. So have a look at the part that I do shell balance. I do shell balance within the here. This is my shell. This is within the pipe. That means I don't have any generation. The only generation I have is here, right? So it doesn't belong in my shell. So that's why I don't have any generation, right? Just because my heater is outside my pipe. And the other thing is I don't have accumulation because it's a steady state problem. I only have in minus out for the pipe, correct? And then if you do this for cylindrical geometry, you find that the QR, the flux at R, times the area perpendicular, the area which the flux is perpendicular to, is 2 pi RL, the area of the cylindrical shell, minus, this is the out, flux times again the area. Okay, but this one is estimated at R is equal to R plus delta R. Okay, this is in, this is out. And I use the convention that this is positive. Okay.
Just a quick question.
Sure.
On the quiz, I don't think there was a letter L that was given. So, like.
Yeah, I mean, and you're not going to need it. The problem is, I mean, so here's the thing. If there's a number that's not given, you can call it any quantity you like. You can call it A, L, whatever. But at the end, that means that the answer is not going to depend on L, right? Your look at your temperature profile. Is there any L here, right?
Okay, thank you.
L is going to cancel already, so that should not be any problem. So it can be of any length. So the answer is not changed by the value of the L. Okay. The other thing is that, so once you get this differential equation, so this is one of the things that most of the students actually found wrong, just because they thought there is generation. There is not generation. There is only generation outside my shell, not within my shell. That's a very important thing. Okay. So if you divide all sides by delta R and take the limit delta R goes to 0 for a very thin, infinite small shell, you get negative of the derivative of the QR times R. Because 2 pi's and L's cancel, you can just like divide by those terms. Those are constant. And you find that the QR times R is a constant. Okay, and you can call it QR2 times R2 because QR2 is given, right? It says in the problem statement that the heater provides a constant flux of Q2, right? So that's basically the Q2 given in the problem. Now another thing is that Q2 given by the heater, let me show it. The heat is dissipated inside, right? I know it for two reasons. It's not actually dissipated outside. There is no heat coming from the heater dissipated outside. It's, first of all, the reason is, well, you can actually intuitively figure this out because this is perfect insulation, right? It's not allowing any heat out. That's one reason. The second reason is, as you're going to see in part II, the shell balance for the insulator is going to give you Q is equal to 0, exactly, which means that none of the Q is actually lost outside. So the entire Q is towards inside, right? If you like work with the absolute value, you can call it minus Q2, depending on which sign convention you're picking, right? Or you can just say that my Q2 is negative, so let me just take it as Q2, okay? Both should be fine as long as you clarify. And from here, you can keep the C1 and like plug in the C1 later if you like. But this is the C1, this is the boundary condition that you need to use. Okay, at R is equal to R2, Q must be equal to Q2. Okay, now if you use the Fourier's law instead of QR, you can plug in this minus K dt over dr must be equal to C1 over R. So you just combine these two things, and then QR must be equal to that. So you can write down this is equal to this. And then you divide by minus K, and then you find this differential of temperature with respect to R is some constant times 1 over R. And you take the integral, basically you multiply both sides by dr, and then you take the integral of both sides, right? And then this gives you dt is equal to right? And from here, after integration, you find this. Okay, because the integral of 1 over R is ln R. And then your boundary conditions, as we said, at R is equal to R2, QR must be equal to Q2. The entire heat generated from the heater must be towards inside. So this gives us the C1, as we said above. And the other boundary condition is at R is equal to R1, the Q conduction must be equal to Q convection. Here you have some fluid, right? It has some heat transfer coefficient H. And you know that the fluid is boiling. Take into account the boiling temperature of the fluid. So you know that the fluid is at a constant temperature TB. Okay. And but you have no clue about this T1. It's not given. Although you can write in your boundary conditions T is equal to T1, you should definitely combine it with the fact that you can solve for T1. So your temperature equation should not include the T1. It should include the TB because it's what's actually stated in the problem. It says particularly that fluid is actually boiling, right? If I'm not wrong. Let's see. Quizzes. Yeah, if the heat transfer coefficient between the boiling fluid and the pipe wall is H. Yeah, exactly. So we know that the fluid must be at its boiling temperature, constant temperature. So this is, this is the conduction at R is equal to R. This is the convection. We use the convention that plus direction is towards outside, right? So this is going to be TB minus T1 to make this positive TB minus T1. If it's actually from here to here, that means TB must be large to get a heat transfer from here to here. Okay. Okay. And then after some algebra, we can solve for this equation because you know dt over dr in terms of C1, right? We wrote it down here. And we write down TB. And instead of T1, you just write down T as a function of R, but R replaced by R1. Okay. So this T1 is the T calculated at R is equal to R1. Good. So after some algebra, you find that the C2 must be this. Okay, and you plug it in the temperature equation, and you find this one. Please let me know if you have any question about this. Okay. In part 2, within the insulator, the flux is 0. The reason is as follows. You can do the following if you like. You do the shell balance, right? Not required since you have already done a similar shell balance above, right? But you should know what kind of equation you should get out of this. This is Q at R, Q at R plus delta R. And then you say in minus out plus generation is equal to accumulation. And these are 0. No heater within the insulator either, right? Because the heater actually resides somewhere here with respect to my shell. And the in is QR 2 pi R L at R minus QR 2 pi R L R plus delta R is equal to 0. Divide by delta R both sides. Take the limit delta R goes to 0. You get negative d over dr. QRR is constant, right? Oh, sorry, QRR is 0. So this tells us that, again, QRR is constant for the insulator, right? But you should argue the following. If this is my, if this is the pipe, if this is the insulator, and if this is the heater, this is the pipe, and this is insulator, we know that here there is no flux, no heat dissipated to the surrounding, because this is perfect insulator, right? That means Q at R is equal to R3 must be equal to 0. So this constant is equal to this evaluated at Q R3 times R3, right? And you know that this is 0. So that means this constant is 0. So it's not any constant, but it's 0. So basically the QR is 0 everywhere. Because this is finite, but this must be 0 because the product is 0. QR is 0 everywhere within the insulator, right? Because in the problem it doesn't say any insulator, it says perfect insulator, that we find that the flux is 0. So dt over dr is 0, so T is constant, which means that T is going to be equal to the T at the boundary. So you can say T is equal to temperature that we had found earlier here, but plug in R2 instead of R1, right? So the temperature of the pipe at exactly R2 gives you the temperature of the insulator at R2, so temperature of the insulator at anywhere because it's constant. Okay? Any questions so far? No? Okay. So for part B, you should write down the resistances. So one thing you can use as the resistance is delta T divided by the Q. And for the pipe, resistance for the pipe is T2 minus T1 is your delta T, right? Divided by the Q. Q is basically the flux times area. The flux is the flux at Q2, so flux at R2, right? Okay, so this is the temperature difference across the pipe, and this is the Q, and the Q is constant along the pipe, so you can calculate it at any point. So I just chose to calculate it at R2 because I know the flux at R is equal to R2. Okay, so from here, if you solve, where is that? T2 minus T1. Have a look at this. Oops. T2 minus T1, you can calculate this from here if you like. The T2 minus T1 is nothing but minus C1 over K times ln R2 over R1. All right. And the C1 basically is nothing but the Q2R2, so you get negative Q2R2 over K. And in the denominator, you have the same Q2 and R2 terms. You can cancel them. You can simplify it to get ln R2 over R1, 2 pi L K. You can say that L is not given. Let me just calculate this resistance per unit length. You can say, or yeah, so you can, you don't need to actually have this L there. I mean, I would actually count it as correct if you don't have that L there, but that's okay. So this is your pipe. This is the fluid pipe interface, and this is the perfect resistor. And perfect resistors have infinite resistances, right? Because you have a similar formula for that, but the K actually goes to 0 for the perfectness. Sorry. K goes to, 0 for the perfect insulator, which makes this quantity infinity. So you should particularly say that the insulator should have an infinite resistance. Okay, so this is for the pipe, and this is for the convection. You can actually write it down from your notes even, or you can redrive it based on this equation if you like. Okay, any questions so far? No?
This question, he goes over a lot of concepts, and he kind of help us understand the material.
Good to know. Yeah, yeah, exactly. I like this types of problems, especially where like most of the people struggled was this part. The generation is 0. So you should actually have an understanding between two different situations where you have, for example, like imagine that you have like a wire that generates heat and no generation here. So I don't have the R dot in my shell balance. No R dot in shell balance. But if you have a schematics like this, for example, generation throughout the entire material, but then the entire material, then you would have the fancy R dots, the heat generation term in your shell balance on one side on A type material. For A, but not B. Okay, so that was important. So any other questions about homeworks or quiz?
Just a quick question about the quiz. I also assumed that it was a steady state, but I don't think the problem specified steady state. Do we just always assume that it's steady state?
Oh, that's a great question. For this problem, there is no sign of being like unsteady state or transient problem, right? There is no mention of time in this problem. There is no mention of how the profile changes with time. There are no signaling words. Like, does it make sense? Like, it doesn't say initially, for example, the pipe which was at T is equal to like 300 degrees is made contact with some other material at time is equal to 0. So that would actually give you a warning that, oh, this is going to be a transient problem because, oh, it's initially it's at this temperature, but it's going to change with time. Does that make sense? So, but in this problem, there is no particular mention of any time change, like change with time, any unsteady stateness, like any two things brought to contact initially at time is equal to 0 and signaling that things are going to change. Does that make sense?
Yes, thank you.
Okay, no problem. Okay, those are really good questions. Okay, how about we go over problem 4? Look at it. It's very much in common with our quiz problem, right? In the sense that whether you're going to include the heater in your shell balance or what does this insulation do to our system, right? So let's have a look at problem number 4. It's very instructive, I guess. Let's say problem 4. A thin heater sheet which provides constant heat flux of 500 watt per meter square. This is the heater. Is placed between two layers of A and B as shown in the figure. This is my material A, material B, and this is my famous insulation. Right? Thermal conductivity of material A and B are given. So Ka is 2 in SI units, and Kb is given as 5 in SI units, right? And the heat flux, so the heater sheet provides a heat flux of 500 watt per meter squared. So let's say constant heat flux Q is equal to watt per meter squared. But to which direction, right? That's the question. So the most important question of this problem is the following. Which way this flux is going to go? Or if it's going to go both ways, how is that going to be shared, right? I mean, is it like, oh, this is 500. Let's say 500 watts per meter squared. Is it like 300 here and 200 here? Or is it like 10, 490 here? So what is the share, right? So that's the very important question in this problem. And the answer is going to come from the shell balance from the A side. Okay, here's the thing. Now, before you do anything, you can just argue, like in the previous quiz problem, you can say, oh, there is an insulation here. So the flux at this surface is going to be 0. Oh, if the flux were the same throughout this entire block A, then it would be 0 here. Oops. It would be 0 here, it would be 0 here, it would be 0 here, and it would be 0 here. So the share would be probably 0 to 500. Right? That's your intuition. And you should get this from the shell balance immediately. You can say that the shell balance from A side is going to give you the following. A, in other words, this shell balance gives you the following. In minus out plus generation is accumulation, steady state 0, generation 0 because my heater is away from my shell. So in minus out is 0, which means that Q times A, Qx times A at x minus Qx times A at x plus delta x is 0. A is constant, cancel. So minus dqx over dx is 0. From here, qx is constant. But boundary condition tells you that at x is equal to 0 here, right? The qx is 0. So qx is 0 everywhere. Where? Within the insulation. Correct? So that's a very remarkable thing. So that tells you the following: the entire heat generated in the in this heater is fluxing to the right hand side. Okay, so you can say that it's basically 0 to 500.
So would the insulation be considered perfect in this case?
Yeah. So here's the thing. Exactly. That's a great question. Yeah, that should be so here's the thing. Now, the problem should have said perfect insulation, but even if it doesn't say, here are the like signals that you actually decide it must be perfect. Now, the problem doesn't give you an idea about the like thickness of the insulation, doesn't tell you what's happening the other side of the insulation. It's not telling you even the conductivity of the insulating material, which means only one thing: probably we don't care about what's happening. We only care about it's just insulated, and let's just take it perfect insulation. Okay, but in some problems, we make it specific that, oh, okay, insulating material like a plastic insulating material wrapped around that with a thickness of, like, for example, 10 centimeters. And if it doesn't say it's perfect, then you should think about the conductivity and what's happening outside. Generally, there might be some mention of like there's air outside of the perfect insulation and it's being cooled by air at like 20 degrees, which has a heat transfer coefficient of like 20, whatever. So those actually signals the fact that you should actually take the conductivity and the thickness of the insulation into account and should not actually treat it perfectly. But that's basically, you're right, that's the problem that's an issue from the problem statement. It should tell you the perfect insulation. But even if it's not, I mean, you can convince yourself very easily that this must be perfect insulation because there's no mention of what's going on beyond the insulator, right? Does that make sense?
Yes. So if it was not perfect insulation, the Q would be going to the right and left?
Exactly. The Q would be actually shared on two sides. Yep. And you can actually solve, oh, that would be a great exam problem, right? I'm kidding. But that, I mean, not for this semester, maybe just because I'm mentioning it. But here, this can be a great exam problem for the next semester, I guess. Imagine that there is heater and there is like this fluid H, C, HD, fluid D, material A, material B, heater. And you're given, imagine that the thickness is L1, L2. And you can find out like how much of the heat is to the left and how much of the heat is to the right. By using shell balances again, finding the temperature profiles and using the boundary conditions. You're going to have, like, for example, one boundary condition here. Oh, it's not a heater. One boundary condition here, which tells you that the convective heat transfer is equal to the conductive heat transfer here. Another boundary condition here. And for this case, two boundary conditions, another boundary condition, the temperature at the right of A is equal to the temperature at the left of B. And another thing is the flux at the right of A is equal to the flux at the right of B. So you have 4 boundary conditions with 4 unknowns, right? And the 4 unknowns would be C1 of the A, C2 of the A, and C1 prime of the B, and C2 prime of the B. And then you can get the temperature profiles for the 2 cases from 4 boundary conditions, and you can get basically the fluxes for the 2 cases. So from the C1 and C1 prime, that would give you how the fluxes would be shared in 2 cases. And you also have another condition which tells you that if those boundary conditions are not enough, tells you that the heater Q is split between Q1 and Q2. So it would say that sorry. Okay, one boundary condition is this. The second boundary condition is this. Third boundary condition is the temperatures are being equal. But the fourth boundary conditions, I actually neglected one important fact, would be Q in the A side. I'm sorry. BC4 would be the following. Q, the flux at A. Okay. The flux for A at X is equal to L1, for example. You can think of it as this flux coming in, right? Minus Q of the B at L1, right? Plus the generation term for the heater, Q. If you divide all by areas, you just get this one, must be equal to this. So you can say that my fourth boundary condition must be Q is equal to the difference between the L1 minus difference between the QB and the QA at X is equal to L1. So that would be my fourth boundary condition. Definitely this and this would not be equal to each other. I'm sorry for that. If there were no heater, yeah, they would be equal, but for this particular problem, it would not. Okay. Is that clear?
Yes.
Okay.
So going back to the original problem, Professor.
Yep.
So if we're saying the flux or the X equals to 0 is equal to 0.
Mm-hmm.
So how is it constant on A if A goes from X equal to 0 to X equal to L1? Wouldn't it just be equal to 0 at X equals to 0 instead of everywhere? Or A is also being considered an insulator?
No. Here's the thing. I made use of mathematically 2 facts. Mathematically, I know that the Qx is constant throughout A, right? That's a certain fact that came from the shell balance, correct? The entire A. That's very important. And I also made use of the fact that Qx is 0 at, here, Qx is 0 at X is equal to 0 in A, right? So if I combine the 2 facts, if Q is everywhere the same, and if Q is 0 at one point, then Q is 0 at all the points, right? It's just like a mathematical fact.
Oh, okay.
So it's like saying, my brother and I have the same age, and my brother is 25 years old. So how old am I? I am also 25 years old because I said that I am also the same year as old as my brother, right? It's the same thing. I say the Qx is everywhere the same, and Qx is 0 at one point. So guess what? Qx is 0 everywhere, right? That's a mathematical argument happening there. So basically, A is also behaving like a perfect insulator. Like very strange, right? But if I didn't have,
Okay.
yeah, if I didn't have any insulation here, there would be some H, there would be some Q going to the left, and that constant would not be 0. Okay. Any other questions? Okay, so let's determine the steady state temperature distribution both in layer A and B. In layer A, the temperature distribution is just going to be this, 0, because you know that the Q is 0 everywhere. This means del T over del X is equal to 0, meaning that T is constant. So this insulation, this is A, this is going to be just T constant, right? And this is heater. And we should find what's going on in B too, right? If you do the shell balance for the B, you would get exactly the Q over dx is equal to 0, right? And from here you would get Qx is constant for the B side as well. Let's call it C1. And then minus D, like minus K, KB dt over dx must be equal to C1. From here, if you take the integral, you would find T is equal to minus C1 over KB x plus C2, correct? And then you know a couple of things, right? So one thing is boundary condition 1 at x is equal to 10 centimeters, or in other words 0.1 meter. You know that the Q is equal to the entire Q generated from the heater divided by the area, right? It's the 500 watts per meter squared, right? But it was constant, so you find that from this Qx is equal to C1, we find that C1 is equal to 500 watt per meter squared. So your temperature equation looks like the following: 500 watts per meter squared divided by KB, and the KB is given, I guess, is 5 watt per meter Kelvin, times X plus C2. Now we should find C2. Let me just simplify this. T is equal to negative 100, and the units is 1 over meter times X plus C2. Okay. Sorry, Kelvin per meter. Yeah. And the boundary condition 2, we say that at the surface here, the H is equal to 25 watt per meter square Kelvin given, and the T air is 20 centigrade. We find that the flux Qx is equal to H times T, let's call this T, TS, T surface. T surface minus T infinity or T air, right? And Qx is given as 500 because it's constant everywhere. We found that this is constant everywhere, right? It is 500 watts per meter square is equal to H is 25 watt per meter square Kelvin. And this is TS is basically T estimated that X is equal to 25, correct? So, yeah, x is equal to 25, which is going to be this thing for x is equal to 25 centimeters, negative 100 Kelvin over meter, times 0.25, sorry, 0.025 meters, minus T air is given as 20 degrees centigrade. Yeah, but so let's, so you want to work with Kelvin, so let's work with Kelvins. That's 293 Kelvin. Oops, what did I forget? I forgot the C2. I forgot the C2. Right? Plus C2, because I'm using this description and this entire thing is coming from this. So I can solve for C2 now, right? So let me get my calculator. You can also work on it. So let's see, that's 20 plus 293 plus 2.5. So C2 is equal to 315.5 in kelvins. So I got it. T is equal to negative 100 x plus 315.5 Kelvin. In centigrade, it's basically T is equal to negative 100 x plus 42.5 centigrades. Okay. So that's the temperature distribution. So it's since it is it has a negative sign, a negative prefactor in front of x, it's a decreasing function. So it's going to look like here. It's going to look like this, and it's going to take the value of what temperatures. You can actually mark them. You can say at x is equal to 0.1 meters, you get T1 is equal to what, 32.5 centigrade. So you basically got this. This thing is 32.5 centigrade. This entire thing up to here. And then this one is x is equal to 0. Is it 0.025? I made a mistake. That's 25 centimeters. I'm sorry for that. This is, oops, 25 meters, correct? So let's do it correctly. 25. So you get 315.5. So instead you get 338 Kelvin, right? And in terms of centigrade, you should get 65. Okay, there you go. And this is 55.
So, Professor,
Yep.
that -100, it has a unit of Kelvin per meter. So if we're changing to Celsius, the whole T, doesn't it affect the -100 as well?
It's an excellent question. Any answer for that? Have a look at this. This is the difference in the temperature. This is the temperature absolute part of it. Or you can think of it as follows. We shouldn't, you must not change the -100x. So imagine the following. Imagine that you're talking about 20 degrees, right? How many Kelvin is that? 293 Kelvin, correct?
Yes.
Now imagine that you just split it into two. You write it as like 200 plus 93 Kelvin, correct? You can write it as such. Correct?
Yes.
Now, if you want to change this to centigrade, for example, do you subtract 273 from both this and this, or just from one of them?
Oh, just one more.
Only one of them, because if you subtract from both, you double subtract, which gives you like a meaningless number. So let's see. To -73 minus, oh, it gives you a negative number, so that doesn't make sense. So if you add something, you just add to the entire quantity. So I'm subtracting the 273 from this entire thing, which means that I'm just simplifying these two. Okay, so you can subtract only from this, but you don't know that, so it's not possible, right? Does that make sense?
Yes.
And also another short answer would be this corresponds to the differences in the temperatures. And also like this thing, like think about the H, for example, H, like 25 watt per meter square Kelvin. This Kelvin corresponds to the differences in the temperatures, not the temperature itself, because you're multiplying with like something like T minus T infinity, right? So in other words, this is exactly the same thing as 25 watts per meter square centigrade. Okay, because the differences in the temperatures for the centigrade is the same as the differences in the kelvins. Okay. Good, excellent question. Thank you. So for this, you get 0.25 meter. T2 is equal to, you get 25, subtract from 65, you get 40. Correct? 40 degrees. So it's a linear line because I know that it's like ax plus b. And then here, this is 20 degrees centigrade. So it's going to be something like this. Okay, so that's the temperature profile. Any questions? Okay, so we answered for both part A and B. And sketch the thermal circuit representation of the system. Okay. So you basically should have something like R insulator is infinity, right? There is another R here. And there is another R here, right? You just write down this R2 is going to be equal to the delta T over Q, right? And it's a linear function, so you basically get T2 minus T1, or maybe let's say T1 minus T0 over Q is nothing but K times T1 minus T0 over delta X, which is like, let's call it L1. Okay, so after these cancel, you just get L1 over K for the Ka. So this is L1 over Ka, and this comes out to be L2 over Kb. Okay. Although this has finite resistance, if you sum the two, this has like infinite. So to the left-hand side, you have like infinite resistance. So that's why the heat coming from the resistor prefers to go towards the right-hand side. Okay, that's the sketch of the thermal circuit representation.